the semicircle maps to what? Maps to the positive part of, or upper part of x, y, imaginary axis. So any semicircle can be maps to the following linear fractional transformation, x1 z minus x2. This is actually linear fractional transformation. You can always write using the SL2 here. Okay, then what happens? And then this semicircle gamma maps to the y-axis, or imaginary axis. Why? Because this mapping x1 goes to 0. Yeah? And x2 goes to infinity. So only possibility is a half line, but which should pass through this origin. So this is the y-axis. Actually, you can check, just like that down also the equation of this circle. Also, you can prove, but you will not calculate anything. Okay, so, and also this mapping does not change the metric. So what you have to prove is, if you have here are the 2 points, P and Q, then this map to somewhere. P prime, it's IKY, and Q prime has a form IK2. This form. So, I want to show that this shortest curves passing, joining P prime and Q prime is this straight line. And that you can show that if you have these forms, then it's strictly longer than this distance. Plus using this form, y square, x square plus u square. Because that this only changes the scale for the y direction. Of course, for the Euclidean case, you know that this is longer than this one. But even this form, this just y direction changes, so you can also show that this is shortest line. Therefore, in a sense, the shortest line is in the Euclidean case straight line. So you can replace that in this geometry straight line. The curve corresponding to the straight line in Euclidean geometry is just a half line or semicircle. But in that way you can prove it. Okay. And now you can play a lot of many interesting things. For example, if you calculate the angle of the triangles, so triangle is now given by these curves. So this is a triangle. Okay? And what is angle? Angle is just take the usual Euclidean angle. Because you know that linear fractional transformation does not change the angle. So, and then you can easily guess that this sum of angle seems less than 2 right angles. You can guess. And actually you can prove it using this linear fractional transformations in a very nice way. Okay, so this is triangle is congruent. So it has the same shape if and only if. So the corresponding angles are the same. It never happens for the Euclidean case. If the corresponding angle is the same, you just get that. If you change the scale, the two triangles become the same, but it's just yeah, there are even too many non-congruent triangles. But in Euclidean case, really the angle determines the triangle itself. So it's a very strong geometry. And I talked too much again, sorry. And finally I have to show that this is basically equal to I don't know what do you use in China. So unit disk is defined this. Okay, so inside of the compress plane, you have equal 1. Now, the point is, this is actually conformally equivalent to the upper half plane, H. This inside is. And this part goes to this axis. So what is the simplest way to go? I always forget. I think this way is easier. What is just by the linear factor transformation, but now in this case, complex coefficient, you can prove that. So what is so this is 1, this is -1. So what shall we do? I forgot. Z. So 0 should go to I hope. So, that's okay? And then the 0 goes to no, this is not correct. 0 should go to I. So maybe this one. 0 goes to I, and -1 goes to infinity, and -I goes to 0. I hope this good. This gives you. Is it true? And what you can get it? Information so that everything goes to the same. And in this case, for the unit circle model, what is a straight line? The line corresponds to a straight line is just a circle, semicircle, intersect perpendicular to the boundary. So again, that you can find that many lines which are parallel, passing to the one point. And maybe you know the picture of the Escher? You don't know? There are sometimes fish, many fishes going to the boundary.
Is it Panda?
Escher.
Is the name of Panda?
Painter, yes. That's painter. 5 minutes pause.
Yeah.
So this circle, or this line, should go to the map 1 and -1 and I. That means that this maps to this circle. For example, what maps to infinite? Infinite point goes to, just take a sort of the limit, go to 1 over -I, so this is nothing but I. So go to here. This is so for the unit circle model, unit disk model, you can see that the boundary point at infinity. It's also the point. So this gives you the
Z equals I goes to
y and 1 minus I, 1 is what you get it. 1, 1, 0, 2i, minus 2i, and 0. So it's essentially equivalent to 1, 1, 1, 1. This mapping is all 0 by 1. And you apply again, you get becomes identity. So if you take 4 times, it becomes identity. So it's a very special mapping. But in this way, that you can show that every non-Euclidean geometry on the upper half plane, you can write down in the non-Euclidean geometry in the unit disk. And non-Euclidean geometry in the unit disk is usually called Poincare model. And he used this non-Euclidean geometry to construct the autonomic function. That's also a great discovery of the end of the 19th century. So it's a kind of the generalization of the modular forms, which I gave in last talk. So my talk started by the fundamental theorem of the Gauss, or algebra due to Gauss, and then almost end by the Gauss theory of surfaces. And his theory was published in the most important paper is 1828. It was written in Latin. And I have a book, Latin and English translation of this. So I think I leave it also here, so that you can read it. And there, Gauss studied the surface in three-dimensional space, inside of the surface. And Gauss pointed out that if you study the surface, there would be 3 different methods. And the first method, different way to express the surface. And one is just using the equation, write down, and something equals 0, or some constant gives you the surface. F may not be the usual polynomial, but maybe more complex function. It's okay. And other possibility is just you write as a graph of function 2 variables, then you get some surface again. But most general way is just you write something UV, so parameterized by 2 variables. And actually, to study it, in this case, this is a very special case of this parameterization, because you can use x and y, UV. So x is x and y equal y, and z is given by gxy. So in this case, it's very special. And also, in this case, you're using the implicit function theorem. You can write in a good place. You can write, for example, z as a function of x and y, or y as a function of x and z, so on, so that you can reduce to the, basically in this case, so in this case. So the most general way of writing the surface is in this way. And moreover, this parameterization is, of course, not unique. There are many, many parameterizations. And even the point is, if you have some surface, you cannot choose a global parameter. In some part, you have some special parameter, and in the other part, you need some special parameter also. And that is, in a sense, that it gives you the very rough idea of the manifold. So manifold is a sort of a kind of the parameterization, but you can choose a global parameter. So you can choose locally some parameters.